the sea. Wherever that river goes, that's where I want to be. Flow, river, flow. Let your waters wash down. Take it from this road to sun.
Okay, my easy riders, we're going to continue now in our chapter on earth cycles and talk about water cycles, water reservoirs, and water currents. You've no doubt seen an illustration such as this, which represents the water cycle. If we start over to the right, you have water in the oceans, and solar radiation from the sun evaporates the water into water vapor. That water vapor can condense to form rain. Of course, some of this water may evaporate from lakes and even from our swimming pools and our daily use of water as we wash our cars, etc. But the water evaporates, condenses as rain. The rain then washes down through streams, collects into rivers and lakes. Much of it is absorbed into the ground, is filtered through groundwater, and can eventually return to the sea or to the ocean. Now, what are our water reservoirs? 96.5%, very large percent of water on planet Earth is collected in the oceans. Only about 1.74%, but an important 1.74%, is in the glaciers and ice caps on the poles. 1.7% is in groundwater, and a much smaller than you might have imagined, percent of water is collected in rivers and lakes, 0.013%. And an even smaller percentage of water, of course, is in living systems. Now let's talk about the ocean and currents in the ocean. Water masses in the ocean move via convection from the equator to the poles, from the hot area of the equator to the colder regions around the poles. And this results in circular movements called currents. It turns out, and we'll see this in the next slide, that in the northern hemisphere, the currents go in a clockwise motion, whereas in the southern hemisphere, they go in a counterclockwise motion. And we'll see that a consequence of this is what we call the Gulf Stream along the U.S. Atlantic coast, and how this brings warm water to our eastern shores. And similarly, we have the California Stream in the western coast of the United States, and this actually leads to colder streams of water in the western states. So here's the map showing these ocean currents. If you focus on the North Atlantic Ocean, you'll see this clockwise rotation. Similarly, in the North Pacific Ocean, you see a clockwise rotation of the ocean currents. But again, notice that below the equator, whether you look at the South Pacific or the South Atlantic or the Indian Ocean, which is hard to see in this illustration, that the currents go in a counterclockwise direction. Looking back at the North Atlantic, we see that this clockwise rotation carries warm water through the Caribbean towards the Florida Peninsula and then up the eastern coast of the United States, eventually making its way to Europe. This is called the Gulf Stream, and of course Columbus traveled the Gulf Stream to come to the North American continent from Europe. You might also note the interesting pattern of ocean currents in the Pacific, where the prevailing pattern can be east to west at certain latitudes and then can reverse and go from west to east at other latitudes, making it possible for seamen to be able to navigate back and forth in the Atlantic Ocean depending upon their latitude. Also in hurricane season, you probably know that hurricanes tend to approach the United States through this Gulf Stream pattern, through the Caribbean, through either the Gulf of Mexico or the Florida Peninsula. This is again due to this prevailing Gulf Stream pattern of ocean currents in the northern Atlantic. A little more about ocean reservoirs. The oceans, the largest reservoir, 96.5% of water on planet Earth, is salt water. The problem with salt water, of course, is that the salt composition is too high for human consumption. I show in a table at the bottom an interesting pattern for salt water, for ocean salt water. The sodium cation is the most prevalent cation, much more so than potassium and calcium. And it turns out that this is just the opposite composition of cations for living cells. In living cells, there's a greater concentration of potassium cation inside cells, whereas for seawater, there's a greater concentration of sodium cation. An interesting observation, and we'll see later on that this is actually a characteristic of living systems. With regard to fresh water, about 1.7% of fresh water, as we said before, is in polar ice caps and icebergs. And there's an additional 1% or so in groundwater, which are available to animals and to terrestrial plants for farming. In terms of personal use of water, our use of water in our daily lives and home usage, we consume about 80 to 100 gallons of fresh water per day for individuals living in North America. Can you believe that? 80 to 100 gallons of water per day, of fresh water that we consume. If you include farming to produce the food that we eat, it's up to 2,000 gallons of fresh water per day per person in the United States. So, maintaining the groundwater, keeping it from being polluted, keeping it from drying up, is extremely important for our way of life. In addition to the recycling process of rain, we also collect wastewater and treat it. That is, most municipalities and cities have wastewater treatment plants. Well, we'll pause now after this brief discussion of the water cycle and water reservoirs. And then in the next slide, we'll talk about what I call the big picture. So see you shortly.
The river flows, it flows to the sea. Wherever that river goes,
that's where I want to be flowing.